Yeah, all right, sweet. Yeah, so we're going to talk about the metaphysics of string theory. So, so yesterday, what you saw was a report on work in progress. Today, I would say that this is more of a report on work prior to progress, and also on something that, like, to be honest, you know, some people here, like perhaps especially Nick, make that ambiguous between Huggett and Tay. That makes sense. Know way more about than me, but you know, you got to go out on a limb if you're going to think about this stuff at all, I think, and so I'm going out on a limb. And this is work done jointly with Noel Swanson at the University of Delaware. In fact, the project was really Noel's idea. He kind of emailed me a year or so ago and was like, I read this survey article on string theory and M theory, and I thought, like, there's low-hanging fruit here for metaphysical interpretation of physics. And I was like, yeah, man, let's do it. And we realized that we needed to, before we started thinking about anything about M theory, we needed to think about kind of like some more basic stuff. So the question for today is, how do we interpret the string Worldsheet, right? And it can be a little depressing how speculative this kind of stuff has to be. So I do just want to start out by like reminding people what we're doing is speculating about, you know, how to interpret a theory of everything, right? So that's a kind of optimistic thing to be doing in the first place. You know, it's like, it's pretty cool that we're in a position to think about this at all, even though, like, you know, maybe the stuff we heard yesterday from, I mean, it's possible that string theory is just like doomed, right? But we'll imagine that maybe it's not for purposes of this. Okay, so I have a couple quotes on the slides, and I'm going to get rid of the slides because a lot of my notes of what to say are on the computer. This is going to be a lot more kind of like half-baked free form than yesterday, so I expect more kind of back and forth with you guys than during the talk yesterday. And indeed, I noticed yesterday that all of the interrupting questions that I had were like super excellent. And that indicates to me that if there's a normal distribution of questions out there in the audience, I'm only getting the very far like positive tail of the questions. So like, you know, let's try and, yeah, so in other words, if those are the questions that met the threshold for people to ask them, I feel like there's a bunch of questions out there that are also amazing that people felt didn't meet the threshold, and you know, like, so set your threshold lower and feel more free to ask questions than you did yesterday, because questions have been amazing. This is true for questions in the other talks as well. Okay, so here's Whitten, right, in a kind of semi-popular article called Dualities, Spacetime, and Quantum Mechanics, where he says, I'm really happy that I'm going after Nick's lecture from yesterday, because Nick presented a lot of great, useful stuff that's going to be background to what I say today. Namely, he presented some stuff about the sort of Polyakov way of understanding the, you know, what we can think of as the displacement of the string in its quote-unquote background space-time as really quantum field theory on the worldsheet of the string, right? And that's really the question for today. How do we understand that picture? And should we perhaps understand it as, yeah, like reality is just this like two-dimensional field theory, right? And the worldsheet is the fundamental space-time. So that kind of picture is suggested by this quote from Whitten. He says, in string theory, this auxiliary two-dimensional field plays a more fundamental role than space-time, and space-time exists only to the extent that it can be recovered from the two-dimensional field theory. Right? The thought here being, yeah, maybe the fact that we do so much of the work with this two-dimensional field theory on the worldsheet is pointing us toward the idea that regular space-time is a non-fundamental thing. You know, some physicists usually use the word emergent from the two-dimensional field theory on the world sheet. For philosophers, I think that's, I'm not going to say it's loose talk, it's a different way of using the term emergence. In philosophy, we would usually call that reduction, right? Usually emergence in philosophy has the connotation that there's something going on at the non-fundamental level that is in some sense like not going on at the fundamental level, which is not a correct conclusion to draw in this case. But I might slip back into an emergence talk, but keep in mind we're talking about reduction here. The idea that the regular space-time we see is in some way reducible to this two-dimensional quantum field theory. Okay, so just to remind you of something that Nick mentioned, right? This two-dimensional field theory is going to take the form of, well, you have I'll just kind of retrace this Hans diagram. I guess this isn't a Hans diagram. It's like a half Hans diagram. So it's an open string. It's like somebody's split their pants diagram. So you might have a world sheet like this, right? And ordinarily, right, we would think of, suppose it's just like, imagine like two axes for external space-time, right, like x1, x2, and then we say, there is this, what we can think of as the displacement of the string at a particular, you parameterize the string by sigma and tau coordinates, right, which are not really, they shouldn't be understood as any kind of real metric on the string. We'll talk about that. Or they're just the parameters on the string, right? Think of parameterizing a curve, except you're two-dimensionally parameterizing something that's a surface. And xi of sigma and tau on this kind of background space-time picture is telling you where in x1 and x2, x3, the space and time, right, where in space-time, each sigma and tau point on the string is located, right? Now, from this kind of world sheet first picture, instead what and this is just what you do as a formal matter of fact when you are coming up with the theory, is you treat these displacements in space-time, quote unquote, as different components of a field, right? And you quantize the field, so you turn these xi's into field operators, right? So you have a field operator at, or really like smeared around probably if you want to be rigorous, the point sigma tau, okay? So we end up with a two-dimensional quantum field, right? Now this is, Nick talked about the Weyl symmetry of this system, right? So that'll come up a fair bit when we talk about Tiziana Vistorini's concerns about this world sheet first picture. But the Weyl symmetry, right, of this system is invariance under transformations of the sort. So if you define some, like I said, you shouldn't take a metric on this too seriously. If you define some metric on the world sheet, gamma, then you don't change anything. It is a symmetry of the system to transform gamma to e to the omega of sigma tau gamma for any smooth function omega of sigma tau. Okay? That's a symmetry of the system. And
you don't mean the gamma up there, right?
Oh yeah, sorry. Yeah.
What? No.
Oh no, sorry. Yeah. Sorry. Gamma should be down. That's right. Sorry. Thank you, Nick. So, make sure people can really see that this is a gamma. Okay. So, invariance, right, leads to this field theory on the worldsheet being what we call a conformal field theory. Right, so this is something that's talked about all the time. You don't really encounter it much outside of string theory because conformal field theories are kind of simple, and in other situations don't have a huge number of physical applications. But a conformal field theory, you can think of it and people use the short form CFT, which usually means a quantum conformal field theory. People don't often talk about classical conformal field theories. Sometimes I've seen philosophy papers that use CFT as a short form for classical field theory. Probably don't do that if you're writing a philosophy paper, just because it'd be super confusing to anybody who's a regular physicist reading it. So a conformal field theory is essentially a field theory where it's set on a space-time in a sense where the metric doesn't carry any physical significance, but there is physical significance to the angles between curves, right? It exhibits conformal symmetry, which conformal transformations preserve angles, but not the metric at all. And so if it's a special relativistic or a special relativistic analog of a conformal field theory, this has the consequence, right? Because what are angles? Well, they're kind of like in special relativity, angles between space-like and time-like surfaces or curves are the causal structure, the light cone structure, right? So it does preserve causal structure. Okay. So in a conformal field theory, like the one that we, the theory, like the field theory that these x's turn into, we have no metric structure, but we have causal structure. So those are kind of the main things to keep in mind formally about the kind of objects that we're talking about. Questions at all at this point? I feel like sweet. Okay. Now, let me just go through the other quotes that I have here, because the question here is then how kind of realistically do we interpret this formalism we're talking about string theory, right? So okay, well yeah, there's some other things I should say about how this is used, but I'll talk about those when they kind of become relevant. So Witten says this two-dimensional field theory is more fundamental than anything going on in 4 dimensions, or in rather 9 plus 1 dimensions, really. Because the thing that's supposed to be less fundamental than the two-dimensional worldsheet theory is the theory in the kind of background space-time, and in superstring theory that's going to be 9 plus 1 dimensions. Right. So here's Abbas Salam writing in another kind of, you usually find physicists going out on a limb a bit more in popular essays. So this is, and one of the things you're going to see is that a lot of the stuff that this comes from is a little bit old. And I kind of wonder, it's hard to tell these things. I kind of wonder if this is a somewhat dated view of string theory. String theory is really fast. The fact that the people discussing this view or writing in the late 80s, it might be a sign that it's not really where the action is these days. But so Salam says, right, there arises an important question of whether the string theories do really represent a whole new attitude so far as fundamental theory is concerned, or whether we're in fact merely dealing with a conventional relativistic quantum field theory, but formulated in 2 dimensions. So that point of view that we are fundamentally dealing with a relativistic quantum field theory in 2 dimensions, which is a little bit, you know, it's a little bit of a less revisionary way of putting it, because we're dealing with a 2-dimensional conformal field theory, right, which is more different from what we think of as ordinary just any old 2-dimensional relativistic quantum field theory. But he says that point of view, the kind of worldsheet first point of view, has been implicitly or explicitly argued for by, he says, Polyakov, Weinberg, and according to this reasoning, the superstring theory can be regarded as equivalent to a theory of fields in a 2-dimensional spacetime. Okay. So there's some people who at least really thought this. Charles Thorne, the other Thorne, besides Kip, says, and this is in an essay, again from the late 80s, on string field theory. Right, so Nick mentioned last time the idea that perhaps what we need is, you know, to understand fundamentally what's going on in string theory, what we need is what's called a string field theory, where you have, you know, like a quantum field theory with creation and annihilation of particles, but where the particles are strings, right? So that would be a theory. The idea would be something like you have a theory where the creation operators built up out of the field operators create strings, and the annihilation operators annihilate strings, right? That would be what a string field theory would be. And that's turned out to be a theory that's pretty hard to really formulate in a way that does much work. Although, you know, there are certainly frameworks that people put forward about what it would be like. So Thorne says string field theory. So he raises, and this is an interesting question, I think, whether this is really the right way to look at it, but he raises string field theory as a kind of competing view for this worldsheet first picture, right? So he says string field theory is brought. This is actually, these are kind of some caveats, I should say, to put it in context, some caveats that he mentions before saying we really ought to work on string field theory anyway. He says string field theory has brought little new insight into the dynamics of string theory. Moreover, there's the general feeling that the passage of a field theory description sacrifices some of the most basic insights, such as duality, provided by the worldsheet approach. From this point of view, the 2-dimensional structure of the worldsheet is more fundamental than the notion of loop space, which is one of the things that, you know, one of the kind of, essentially like the formal structure that people think string field theory should be, or people thought in 1988 that string field theory should be formulated then, might be central to the final formulation of string theory. And yet it has been very difficult to envisage with the worldsheet approach a formulation that does not rely in principle on the perturbation expansion, right? So this is one of the things that's going to be relevant in the discussion that I talk about. You know, some of the considerations that Noel and I think might bear on whether this worldsheet first picture is a good interpretation of string theory. You know, this is why Thorne says, like, we should stick with string field theory. It's difficult to see how to understand this except purely in perturbation theory. And I don't know, some people have different views about perturbation theory, and for a more sort of realist picture of it, you could talk to somebody like James Frazier or Mike Miller or Porter Williams. But to me, it seems like if we have only a perturbative picture of something, and we don't see how to turn it into a non-perturbative picture of that thing, that's a pretty unsatisfactory situation, and we shouldn't really be a realist about the things that seem to be artifact of the perturbative formalism, right? Because they are just artifacts of something that's merely an approximation to what is really going on. Okay, so those are the quotes that kind of are meant to motivate you that this is a view that's like in the air a little bit, or has been in the air in the past, and kind of deserves evaluating. Okay. So what are the reasons for being tempted by this picture? Right. Well, Thorne mentions one of them, which is it would be nice to have a kind of like duality invariant picture of what's going on in string theory, right? So this gets tough with ADS-CFT if in fact ADS-CFT turns out to be a real full-on duality, because like what is invariant under like changing the dimensions of space-time by saying that like really, you know, like the world is equivalent to its asymptotic boundary, right? That's like what are the things that the world that we ordinarily think of and its asymptotic boundary have in common? What would be invariant under that kind of transformation between the two dual theories? Like God knows. But right, so that might be one of the reasons why people aren't talking so much about this anymore, because maybe it needs to go out of the window. I'll bring that up later again as kind of relevant consideration. Maybe this needs to go out of the window if we really take seriously the holographic duality, right? But for some other dualities, this picture looks pretty good if we say like really fundamentally what's going on is, but by the way, I should say like relevant to ADS-CFT, this is the fifth theory of the x's. Just to be completely clear, this is probably fairly obvious to you guys, but just to be completely clear, this is a conformal field theory, but not the conformal field theory mentioned in the ADS-CFT conjecture, right? It's two different places that conformal field theory comes in string theory. Okay, so here's one of the things that you might like about this picture, where reality is fundamentally a CFT on the worldsheet. You might think like, well, look, you know, one of the you know, kind of like rigorously established dualities in string theory is T-duality, where you take the target space or the background space that the string lives in, and you know, it has some compactified like radius, right? It's you know, the higher the dimensions beyond the regular 4 are rolled up, and you switch the radius of those dimensions from being really small to being really large, or vice versa, right? You take r to 1 over r. You take the radius of those dimensions to 1 over r. That's a duality. The CFT on the worldsheet is preserved by doing that, right? But you know, any picture of the string as living in that background space-time is obviously not preserved. You know, the features of the string as it exists in the background space-time are not preserved by that transformation. So that's pretty cool, right? You have something that's invariant. Yeah.
So it's going from a type 2A to a type 2B string theory. I'm just wondering whether you have preservation of the worldsheet going from between these two types of string theory. So you change the string coupling, for instance.
Yeah. Okay. I mean, maybe I speak too quickly there. Like.
At least in superstring theory. So if you're in the bosonic case, I'm not sure. But in superstring theory, you would go from type 2A to type 2B.
Yeah. No, maybe that's right. Maybe that's. Yeah.
And you could.
Really interesting. It's entirely possible that that's actually wrong.
And you could, if that argument went through, then you could say the same in the context of ADS-CFT, saying this is actually open closed string duality, and then maybe you could get something along the same lines. It's just because the way we usually represent ADS-CFT correspondence, it's a relation between case theory and string theory, but it's could be seen as an open closed string duality instead.
Good. That's really helpful. Yeah. Okay. I mean, as I said, right, this is like a presentation of work prior to progress. Yeah. That's really helpful. Okay, so maybe that's a bit too naive of a picture or way of understanding this. So Yeah, good. So maybe that's not, and especially right. Like I said, right. Yeah, it's so it's probably the case that you would need to replace this with some kind of like you know, restriction of it to some privileged subset of quantities that you define, or something. It's like not like all the quantities are at least going to remain unchanged under ADS-CFT if that's a real duality or something, right? So in a way, it's a bit. It's either a bit outdated or just a bit false to suggest that this is really a duality invariant way to talk about it. That seems correct. So let me not really rest anything on that. Another thing, though, that you might think is it is really nice to have tractable pictures of reality, right? And it's, you know, one thing that is really nice about this is that conformal field theories are really well controlled and understood objects. You know, there's some of the few quantum field theories where the rigorous mathematical version of them that even a mathematician would be happy with is essentially like a fait accompli. So that's a nice thing about having this kind of picture. I mean, another nice thing about the picture really is like, you know, so let me make a move that is a little bit David Albert-esque, right? The picture just kind of jumps out at you. It's, you know, to borrow a phrase from Albert, it's the most obvious and flat-footed way to understand what the theory seems to be telling us, right? To borrow a phrase from elementary quantum metaphysics, where Albert says that about the configuration space formalism of quantum mechanics, right? I think that's essentially the motivation that's behind what Whitman is saying in that quote. This is the most obvious and flat-footed way of understanding what is going on here. Okay. Now, that said, right, there's some weird puzzles that might happen. I mean, and it may be that they would only happen in really idealized toy examples that are not like what the real physical world is. But for example, let's suppose you have two strings that never scatter off each other. Right? So you have a world where there's this world sheet, and there's also this world sheet, and they don't really ever encounter each other or like merge or divide from each other or anything like that. Does this picture then say you have a reality that has kind of like two disconnected parallel spacetimes that have no real relation to each other? That's kind of an odd feature of this interpretation. I mentioned this, so one person who, at least last time I talked to him, is a little bit of an advocate of this interpretation is Keizo Matsubara. And I mentioned this to Matsubara once. I was like, what do you think of this? And what Keizo said is, well, what we expect in a realistic situation, and again, this is another thing that I'm very thankful to Nick for getting into in his lecture yesterday. What we expect in a realistic scenario is that any strings in a realistic solution are going to be interacting with a big background of strings in the graviton state. And so it might be that it's not physically realistic to suppose that there will be any cases where strings go through their life without ever interacting with the whole muddle of other strings. On the other hand, my experience is that in quantum theory, there's always a very small amplitude for anything you could imagine to happen. So I kind of feel like it would be, you know, this is all speculation in a way, because we don't have, what we have now is just a perturbative picture of what's going on with these things. We don't have a Hilbert space picture of interacting states for the strings. So we don't really know what are the generic or non-generic features of the interacting Hilbert space for strings. But it's an interesting question, right? Like, you know, I don't know. I don't know whether to doubt or be optimistic about whether you'll ever get situations like this with a string that just lives off on its own. But that would make this picture pretty strange in a way. I don't know, maybe not the strangest. They have disconnected spacetimes in the same universe in some sense. I don't know. So anyway, that's just one kind of preliminary odd thing about this picture. Probably another good place for questions or thoughts about, yeah, Sebastian.
So I don't know much about string theory at all.
Yeah.
So I'm trying to.
Yeah.
You started by saying that there is the theory according to which space-time is reducible to strings. No, I was imagining if there was possible a way there is just one string. Say, is
Yeah.
that possible? And then like you could run this kind of argument about is it possible a world where there is space-time but not strings? Probably not in this view, but it seems
Not on this
possible. The other way around, it seems possible. It seems that there could be a weird world where there is just one string or two strings, and maybe there is no space-time there or something like that. And so maybe this could be an argument for the fundamentality of the string.
Yeah, I mean, right. So this gets to some of the stuff that came up in Nick's talk again, right? So I think if I understand it right, but Nick can correct me if this is false. What people are kind of hoping for. So what exists now is a perturbative picture according to which you define some background space-time, and then you note that the strings in the graviton state are going to act like deviations from that background space-time to a different space-time geometry, and so they act like they are, changing the metric, right? And then what you hope for is that in a non-perturbative version of the theory, there's no background space-time that you need to include. Instead, that's all going to be a big coherent state of graviton strings. So if you were to have no big coherent state of graviton strings, then you wouldn't have like a space-time.
Yeah. On the sourceless case, right? You just have a thing. There's nothing, you don't feel there's nothing producing gravitons, there's no gravitational sources. It's just an empty universe.
Yeah, that's an interesting, right. So would you have like graviton strings in an empty universe? Right. The answer, yeah, that's interesting. Yeah.
So it's the thing in that. So at least if we're to take seriously the derivation of Einstein equations in string theory, I think that most string states would not have a classical space-time dual. So of course it depends on what you mean by there being space-time. But for instance, in ADS CFT correspondence, we know a lot of CFT states that doesn't feature classical ADS space-time dual. So I'm just thinking, well, of course there's a lot of string states that don't have a space-time, that doesn't feature a space-time in the way we would think of space-times as something describable by Einstein equations, at least. Presumably we would have superpositions of space-times and all sort of weird things.
Yeah, absolutely.
Even if you could reduce space-time, get rid of space-time in the sense as a background structure, you still have the worldsheet as a background in theory, right? You had to erase that.
Yeah, on this picture, on this worldsheet first picture, you would have the worldsheet as a background. So people might then complain this isn't a background independent theory because you have a background, namely the worldsheet, right? I mean, there's a sense in which it would probably this gets this into a question. There's a sense in which it would probably be background independent in the sense that there's like not a fixed background because you could have multiple different worldsheet topologies, right? It could be this one, or it could be this one, or it could be more likely like much more complicated ones. Or surely it would be a rigorous non-perturbative string theory would have an interacting Hilbert space that was a superposition of different worldsheet topologies, right? So in that sense, you might say it's background independent because like there doesn't have to be one fixed worldsheet. There could be a superposition of different worldsheets.
So to get the dynamics of this relation, you have to go to string theory. That's the idea. I don't know.
I think that's kind of an outstanding question, but a lot of people think that that's the idea to do. Yeah, it's interesting. Yeah.
I'm just wondering about the original worry. So the worry is if we have a worldsheet which is a string which is decoupled from other strings, right?
Yeah.
Then you have to think of it being in some of its own space-time, right?
Yeah.
And how far is it different from like a biometric scenario or so in a geometristic story where, say, one metric is coupled to these fields, another metric is coupled to other fields. So.
Well, yeah. I mean, in that case, you would have the different metrics sharing some. I mean, they would share like a set of points, for example.
Yeah.
Right. In this case, you don't have that. So.
It's true, but only under the assumption, of course, that you commit then that the manifold points on their own mean something, right?
Yeah.
So,
Yeah.
I mean, I think your work is very much in
Yeah.
this direction, right? If you have interaction between stuff, then this counts as being a one space-time, but it could very much be that the scenario is such a you have this interaction defined. This kind of set of interaction defined on the manifold, that kind of interaction on the manifold, but both on themselves constitute independent space-time structures.
Yeah, I mean, Niels is referring to a thing that I said in response to John Norton's 2008 paper, where he says he took this as kind of a reductio against a dynamical approach, where he said, well, if this is really true, then if the fields are non-interacting, then they're going to inhabit their own space-times. To which I said, yeah.
Yeah, interesting.
That's about it.
Yeah, I can see how this fits into your view, and I guess, yeah, I mean, like, this gets to one of those sort of space-time functionalism questions where you might think it's like a bit of a definitional question, but yeah, like, right, it's probably a bit like the question of whether in a real parallel worlds theory, with like lots of stuff that's passing through us all the time, is that the same space-time that they live in, or is it two separate space-times, right? Like,
yeah, and I don't think there's any a priori reason to think that it should be the same space-time if the concepts interact with each other.
Yeah, you might think actually, it's totally off topic, but you might think about how your kind of picture applies to something like the many interacting worlds interpretation of quantum mechanics, actually, because that might be a case where you would be inclined to say that there are multiple spacetimes, but somebody else might be inclined to say there's a single spacetime. But interesting, right? Yeah. So on that kind of picture, maybe we should be cool with the idea that there could be a single universe with multiple spacetimes in it. In which case, this isn't too weird, right? I'm not necessarily saying it's too weird. I'm saying it's at least somewhat weird, and it is something that might be a consequence of this kind of picture. Might be, right? It gets to that question of whether there are going to be states like this. But yeah, I mean, yeah. Nick, did you have thoughts though about this issue about whether it's going to turn out that the whole background is made up of strings in some sense, and there's not really any background? Is that because that was kind of what Keizo was suggesting when I was talking with him about these kind of examples.
So coming from the talk yesterday, I mean, even in the picture you're thinking about, of course, you have this, at least formally, the Minkowski metric in the action, right?
Yeah.
So his suggestion was that would also turn out to be sort of derivative?
Yeah, I think that he thought that the fact that you have a background spacetime in any sense in string theory was an artifact of just perturbative string theory.
Yeah, so I think that might, if you really knew what the true degrees of freedom were and how to formulate it, then you'd sort of see where that was coming from as well.
And so maybe you wouldn't want to say that they're graviton states or something, but is it the case then that on that view, like instead of Minkowski space as like the quote-unquote background, you just have like a state of strings that behaved like Minkowski space in some sense?
A state of something, yeah.
Yeah, I don't know, it's interesting, right? Okay.
So I was going to say,
yeah.
So I'm not sure about, so just two things about the discussion. So I'm not sure about these sort of separate strings that don't kind of connect with, I mean, there's a similar thing in field theory, right? If you have terms that are like bubble terms in your Feynman diagrams, they get cancelled out by, I forget how it goes, by sort of when you sort of normalize the amplitudes.
Okay.
You get a term that kind of cancels those out. So I would have thought the same thing would happen in string theory.
Yeah, interesting.
Also, of course, I mean, when you draw a picture like that, you're just considering sort of one term in the expansion, it looks like. I mean, you know what I mean? There isn't just sort of like a single classical string where this is happening. If you're really thinking about the perturbation theory, there's a sum over all the possible kind of topologies that you can have. So
Totally. So that was something that Noel and I wanted to kind of bring in.
Okay.
You know, so because this is a good place to talk about that. I mean, so one real cautionary note about this kind of picture is, let me get rid of this as a distraction at this point. You know, we can talk about it some more later, but yeah, maybe you're right that it will just, you know, I mean, because it's like, I don't know, is it, if you have, like if you have an interaction that has like asymptotic freedom or something, is it really the case that you can't have disconnected systems that just aren't interacting via that? Or, you know, you see what I mean? Like,
oh, I see. I mean, I was just thinking like just a loop that just sort of was sitting there on its own, but...
Yeah, I mean, I guess I would have thought that it was an artifact of the approximation methods you're using.
So my 2 points come together then, I guess. Maybe that's true for some of the diagrams, that you'll have disconnected parts, but some of the diagrams, everything will be connected.
Yeah,
right?
yeah.
So...
Yeah, good. Okay, so one of the things that we're doing when we actually use this stuff is, you know, we don't, I've repeated a couple times, we don't have an interacting Hilbert space for string theory, right? What we do have, and the way that this stuff gets used, is in a kind of, I mean, a mathematical physicist anyway would consider it a sort of halfway house, in the following sense, right? If I want to talk about scattering in string theory, what we have is so this treatment is taken from Polchinski's book, which is probably the clearest string theory book overall. You have a single string Hilbert space, right? And of course, that's going to be a worldsheet that doesn't have any splitting or joining. It's going to be field theories on a worldsheet that doesn't have splitting or joining. And what you have is instates on a Fock space built from that single string Hilbert space, which is H direct sum, H cross H, etc., right? They're taken to out states on that same asymptotic Hilbert space, right? And we have a method for figuring out which in states go to which out states by, now this is where we use these interesting connected worldsheets because we essentially do the analog of the path integral formalism, right? And we say we're integrating, so the in states go to the out states with amplitudes given by a path integral over all worldsheets. Right. So that's where we use the more complicated worldsheets. In the only actual Hilbert space of states we're using here, we really just have the simple single string worldsheet and tensor products of states that are on that simple single string worldsheet. That's the only real Hilbert space we're using here. Now, it's not a Hilbert space that one would expect to be the Hilbert space for any realistic physical system, because it's the asymptotic scattering space, right? It's the space of the states. If we assume, idealizing that scattering is the only thing going on in the world, it's the space of states at the infinite past and states in the infinite future, right? So none of what's being employed here is especially close to what we would expect to be a formalism that can really be given an ontological interpretation. In other words, like what I'm gesturing at really are the same problems that exist for realistically interpreting the path integral formalism in regular quantum field theory. And I'm suggesting like it's not an especially, well, if you come up with an ontological interpretation of theory that is based on something about the path integral treatment of scattering, that's really unlikely to be, in precise detail, an accurate picture of what's going on in the world, because what's going on in the world is probably going to be something that's been described by a Hilbert space of interacting states rather than a Hilbert space of free states which are connected by these sums over histories. Okay. So, yeah, so that's a general worry about this picture, which I think is related to the thing that Thorne suggested. You remember in that quote from Thorne, he said it's difficult to envisage within the worldsheet approach a formulation that doesn't require, or that doesn't rely in principle on the perturbation expansion, right? So he's saying like, we have only a perturbative, which is to say approximate understanding of the worldsheet as, in some sense, like a space-time. We don't have a real interacting theory for students, right? And it's, you can guess about what that would be, and it might be, so one natural thing for it to be perhaps would be superpositions of states with all the possible different worldsheet topologies, right? Nobody ever, to my knowledge, has like actually come up with an interacting string theory that uses a Hilbert space like that, but you might think it's plausible that you would end up with a Hilbert space like that. So that's one of the things, and in that case, right, it's something that Noel and I are still talking about how we would be inclined to understand, but, people talk about superpositions of different spacetimes in kind of like basic naive quantum gravity, and that's something that we feel like we understand. So maybe this would be a case where you would have superpositions of different, basic spacetimes in the sense of them being worldsheets. Right. So that might be the ultimate picture, but it's very speculative to say, yeah, ultimately they'll find a formalism according to which reality is made up of superpositions of different worldsheets, and quantum field theories on those worldsheets. But if that is what turns out to be, then maybe that's a picture that's amenable to this kind of interpretation. So that's all by way of just pointing out that as it exists right now, this kind of picture rests on idealizations, and you got to ask, is it going to be maintained when the idealizations are taken away? Yeah.
So I think I'm picking up what you're saying. I just want to sort of point out the difference between sort of terms that are summands in a Feynman series from superposition, the quantum superposition, right?
Yeah.
Sorry, were you saying that?
That's what I'm saying. Yeah, exactly.
Okay.
Like, if we had states that were
Okay.
real quantum superpositions. Good, okay. That's a really helpful way to sort of figure out a way to rephrase what I just said, maybe more clearly. If we had a space of states that were real quantum superpositions of different world sheets, then it would be a lot easier to start trying to implement this world sheet first interpretation of string theory. We don't have that, right? It's not 100% clear that that's the right way to proceed. What we have is a sum over histories of world sheets, which is not the same thing as a superposition of world sheets, right? And in the case of a superposition, I think it's a lot clearer that quantum superpositions are the sorts of things that are amenable to physical interpretation, whereas sums over histories seem like the sort of thing that are essentially and ineliminably an idealization that is trying to point at, or get to, aspire to a picture that where you have real superpositions of interacting states, right? So when all we have is the sum over histories, it seems highly premature to give an interpretation that would make sense only if we had the superpositions of interacting states. Is that?
And I'd also add that these histories, almost all of them, are really horrible histories.
Yeah.
They're not on
even
mass shell. They don't satisfy the kind of physical kinematic constraints of the theory. They have internal they have the auxiliary metric, right, that you mentioned, that's not compatible, that doesn't have a causal structure that's compatible with the background one. That's even before we start adding over the topologies, because and then they're discontinuous, like I'm sorry, not everywhere differentiable, kind of like the particle ones, I would imagine. So they're pretty horrible histories. I mean, really the question, this is just so what you're raising, it seems to me, is a version of the kind of arguments people raise against the existence of virtual particles. Because that's really what these histories are. They're kind of virtual histories or something.
That's exactly. Yeah, I think it's very parallel to the concerns that one, I think, can reasonably have about the interpretation of the path integral version of quantum field theory, which I think it would be somewhat crazy to say that path integrals are physically illuminating in any kind of sense that we could interpret.
So I have to say, I'd kind of like to be able to be more real, figure out a way to be nice and be realist about virtual particles and these things.
Yeah, it would be cool.
But
I don't know about the prospects for it, but because, like you say, right, it's not even true that, so take, for example, the path integral. Take a quantum field theory for which we have an interacting Hilbert space picture, right? Take one of the handful of quantum field theories that have been actually constructed as interacting Hilbert spaces. You could write up, a path integral version of that, and it's just going to turn out that the states, quote unquote, that show up in the sums over histories of those path integrals don't generally bear any relationship to the states that show up in the superpositions of interacting states in the rigorous field theory. And indeed, like a lot of the states that show up in the path integrals are going to be states that are not allowed to exist in those superpositions for the reasons you said, right? They're just not going to obey conservation laws and stuff like that.
I'm sure it's like all of them except a measure zero set or something.
So in that case we have, you have the path integral picture and you have the Hilbert space picture, and it seems to me that it's bizarre to say we should realistically interpret the path integral picture because that involves like throwing out the Hilbert space picture. I feel like. It seems to me like in the cases where we have a Hilbert space picture, it's bizarre to be at all a realist about the path integral picture, and so, it would be really sad if it were impossible to have a Hilbert space picture of string theory, if if it were, maybe I would say like, yeah, then we should get realist about the pattern. But like, you know, I think it's a healthy conjecture to say that there could be a Hilbert space picture of string theory. Yeah.
And just a question, I mean, the passing of a picture is not per se perturbative, right? It's just that we normally cache it out perturbatively, right?
Yeah. Right. So it could. Yeah. Right. So. Right. Yeah. Good. Because of course you can do it for theories that are even known to exist exactly. Yeah. That's right. Good. So in a way that's that. Yeah. Thank you. That's really helpful. Yeah, because the point that I made in a way, I was suggesting that it was connected to this point that was made by Thorne, but actually it's not really connected with it. It's kind of a separate point. Like, it's equally true that we don't have a non-perturbative picture of what's going on, but I would say that even if we did have a non-perturbative picture of what was going on, if it rested on just the sum over histories formalism and didn't have a real space of states, then I would say that there was a further problem for interpreting it realistically. So good. So it's really a separate issue.
Thanks, Nils. I think I was running path integral and sort of, despite
I
laboring the
was totally
distinction yesterday, I was running the two together.
Yeah, I was totally doing
Although
it,
I think
and
everything
I should have been
probably
warned about what you said.
true as both.
Yeah, can I make a small comment about what I take to be the majority view of the intended domain of application of the path integral picture?
Yeah.
Modulo fringy views, which are interesting, like Faye Dowker and Raphael Sorkin's program. I think they do have some realist aspirations, actually.
Yeah, I don't know much
I think
about that.
right. So most people think of it as a quantization machine.
Yeah.
Right, that's the intended domain of application for the path integral. So if you treat it the way it's usually treated in these kinds of cases, you would say, well, no, it's not supposed to. You're not supposed to interpret these paths.
Yeah.
It's like any. You should interpret it the way you interpret any other kind of quantization.
Yeah.
Right. Insofar as quantization as an interpretation, but it's a way for forming the observables and getting classical limits smoothly in some cases.
Good. Yeah, I mean, right. Yeah, I think. I mean, you might add the caveat that among people who think about this rigorously, that's the consensus, because I do think there are a lot of people who speak pretty loosely about path integrals. But yeah, I mean, so do you take that to be in tension with? I mean,
Anything you're saying?
Yeah.
No.
Yeah.
Sorry. But, right. Sorry. Only superficially that.
Okay.
One can raise a question about it. Trying to make it do work it was never supposed to.
Yeah.
Do.
Yeah. No, that's right. I mean, so then my concern is that my in a way my worst concern or my most troubling concern about this Worldsheet first picture is that it does rest on making the path integral formalism do more than it's supposed to do, because that's the place where the place where the Worldsheet CFT really comes into using string theory is you do path integrals using the Polyakov action, right? But if nobody in their right mind thinks that you should be realist about what's going on when you do path integrals, then why on earth would this be a natural interpretation of string theory? Good. Yeah. Good. So this is really helpful. This is I'm not sure whether anyone else in the room is benefiting as much as I am from this discussion, but I'm benefiting hugely from this discussion. So thank you. And,
sorry, just one more question. So if we're summing over these the action picture, right? Is it like summing over the histories or like summing over Feynman diagrams?
Histories,
Right.
right? Yeah.
Because we are just okay. You shouldn't think of them as famous, but more like history.
Yeah. I think that's right.
Yeah. No, I'm just wondering. Yeah, I'm just wondering.
Is that's right?
So what do you mean by his?
I mean, yeah.
The terms in a Feynman expansion, not in the sum over, in a perturbative expansion.
Yeah, like the different field configurations, right? If you do passing it over the field configurations.
No, so these diagrams correspond to Feynman diagrams.
Oh, they do correspond to Feynman diagrams.
Yeah.
Yeah.
Ah, okay. Okay, so but then it's not the same like it's the same like sum over histories, no, right?
Wait,
I
but aren't
think
you
not in
aren't you summing over histories of the possible like world sheets together with, you know, like X fields, right? Is that not true?
Yeah. I mean, it's
Yeah.
so. I mean, in the same way that you sum over you sum over all the different Feynman diagrams, right? Or you sum over, and then within each Feynman diagram, there's an integral that's basically a sum over all the momenta that are free in the diagram.
Yeah.
All right. Ah, okay. Uh-huh.
So there is a sum in the
Right.
perturbative term.
Right.
But
So it's
these are not the configure. These. But that's kind of good. I mean, what I was sort of trying to say was missing from the theory yesterday is, so in field theory, the non-perturbative path integral takes you from classical field configurations to classical field configurations. The Feynman diagrams are from incoming momenta to momentum eigenstates to outgoing momentum eigenstates. For the string, you have the analog of that second thing, but what you don't know is what the analog of the classical field configuration is.
Mm-hmm.
yeah. I mean, so if let me make sure I'm getting this right though. Like, so what's suppressed in the case of summing over all the world sheets, or what's hidden in the case of summing over all the world sheets? So in the case of summing over all the Feynman diagrams, what's hidden is that you're summing over all the possible momenta for that diagram, right? In this case, what's hidden is that you're summing over all the possible xi fields for that world sheet, right?
Yes,
is that correct?
that's right. Of course, to actually do the calculation, you then apply perturbative techniques to those fields on the world sheet.
Yeah. Okay, good. And so that's the sense in which you could do this non-perturbatively if you had the power to do so, right? Yeah. Okay. Great. That's like I said, right? This is very helpful to me. Okay. So.
Right. There's two perturbative series that you kind of have to do to calculate anything.
Yeah.
One over the world sheets, and then one for each particular world sheet, which is over the
overall
field,
the CFT
CX fields.
Ah, okay.
Yeah. Or all the CFT histories. Yeah. Yeah. Good. Okay. Great. So there were a couple of other things. I mean, essentially, right. You know, I hope you're getting a picture from this that is kind of pessimistic about this interpretation of string theory, because I think that's essentially where we should be, you know, and like I think I'm taking it seriously because it's one of the few really concrete proposals that have been put on the table for how to have an ontology for string theory, but it seems like it's not necessarily the most plausible. I wanted to raise a couple of other considerations that are problems, and one that Tiziano Vistorini has suggested is a problem, but that I don't think is actually that bad a problem. So one thing that's a problem, and we talked a bit about this before, is it's not necessarily true. So one thing, I'll put this in terms we were talking about before. What you would like is a duality invariant ontology for string theory, right? At least, you know, I'm not necessarily as committed to this as some people are. The consensus seems to be that when you have a duality in string theory, well, there's two different ways of looking at it, right? So one way of looking at it is the way that they tend to think about T-duality, which is that you should think of the things that are invariant under T-duality as the real stuff. On the other hand, the way they tend to think about ADS-CFT or the way that some people seem to talk about ADS-CFT is that you should see one side of the duality is emerging from the other side, right? So the conformal field theory on the boundary, we should reduce the stuff that's going on in the bulk to the stuff that's going on in the conformal field theory at the boundary. Nick has a nice paper suggesting that is not really the best way to see it, and that we should really see those dualities as also, just a situation where we want a duality invariant picture of what's going on, if I understood you correctly. So what we really like is a duality invariant picture of what's going on, and this maybe it can be rejiggered into a form that's like invariant under some dualities, but it doesn't seem to really be invariant under ADS-CFT, right? So that's a problem for this picture. Another concern is in the case of the conformal field theory on the string worldsheet, we have a nice way of understanding that. We have polycom action. Famously, there are lots of new objects that have shown up in string theory, the DN branes, right? So D branes are something that showed up in string theory as a result of people understanding the implications of T-duality. Branes are these things that are kind of like, there's strings with more dimensions. They also have some properties that are somewhat different from strings because they can be the endpoints of strings. So you have, branes of different dimensions in addition to the strings now. And I don't know of any, and I've asked a couple of string theorists, they don't know of any versions of string theory where you can describe those branes using conformal field theories on the branes, right? So, in a sense, this picture, if it's going to work out, it's got to be really incomplete in its present-day incarnation because it's really just, it's describing conformal field theory on the strings, but the strings are not all the objects in string theory anymore. You need to describe the branes too, yeah.
But isn't the CFT of the ADS-CFT correspondence precisely CFT on the DN brane? Original in Mendocino's original derivation, it's the open strings inducing gauge theory on a stack of D3 branes, I think.
Yeah.
I'm just wondering. So at least in that picture, it sounds as though this is precisely a CFT for the brane.
Interesting.
What happens in the heuristic argument is that when you put a stack of D branes together, then it starts looking like you have gauge theory. This is a remarkable calculation. Yes, you can actually get emergent gauge. But that doesn't mean the CFT of ADS-CFT is defined on the branes. The CFT of ADS-CFT is defined on the boundary of asymptotically ADS space.
So we did discuss it. It sort of depends on how serious you take the original derivation, I think.
Maybe that is off.
No, I mean it's not off topic. I think it's on topic because if there is a way of understanding branes using a CFT on the branes, then that's really good for this picture, right? And if we don't have one, that's either bad or a promissory note that this picture needs to fulfill. Okay, I wanted to talk also about the concerns that Tiziana Vistorini raises, which are sort of more interpretive and philosophical a bit. So she suggests that the conformal symmetry of the worldsheet field theory should militate against a kind of space-time interpretation of it. Right, so she points out some of the stuff that I pointed out early on, which is that there's no physically significant metric on the string worldsheet, right? It's all there is at least file transformations of the metric make no difference, and so one of the implications of this, which Vistorini points out, is that there's no quantifiable proper time on the string Worldsheet, right? So you might think, so tau is the parameter in the time-like, it's the time-like parameter on the string Worldsheet. And you might think we could define the notion of proper time using it. But because the metrical properties aren't really invariant, you can't talk about quantities of proper tau time along some curve on the string or something, right? Or curve on the Worldsheet, I should say. So she suggests that this is, it's not 100% obvious to me from what she says in that passage from your dissertation, which I think is one of the more in-depth discussions of this Worldsheet first interpretation. It's not 100% clear to me from what she says whether she thinks this is like a really serious problem for this as an interpretation, or whether it just means that this is a really, really revisionary interpretation. But she says, we can't think of tau as being anything like you usually think of time as being, because there can't be quantities of tau in any kind of real sense, right? You can have orderings in tau time, because remember, the causal structure is preserved by conformal transformations. So that's real. Like what is in the tau future of what on the Worldsheet? That is an invariant fact. But how far in the tau future something else is from one point on the Worldsheet, another point on the Worldsheet, how far in the tau future of this point is this point? There's no facts that matter about that. Right?
Can I actually,
Yeah.
Dave, sorry, this raises a second. I wanted to ask you earlier about if you, in this previous discussion about essentially the S matrix, right? If you were serious about the S matrix, when you literally write down S matrix formalism for this, because there is no scale on your Worldsheet. So usually when we write down S matrix formalism, we have a scale.
So what's the definition of asymptotic future?
Exactly. Yeah.
Yeah, I take it that the definition of asymptotic future is, right, that's,
you could have in and out. There's no problem just saying in and out.
yeah, you say in and out.
But literally asymptotic doesn't really.
That's a really, I guess, so there's a sense in which asymptotic makes sense in these diagrams, right? Because you can think of it as like, what are the topological holes in the Worldsheet? But
that's not in general.
But interesting. That is a really interesting point, Nick, that I had not thought of, and is very relevant here. Good.
But that's exactly right. When you try, you think about doing a closed scattering, and you have sort of the tree diagram, you kind of have a sphere with tubes coming out of it. You just conformally contract it, so you just have a sphere with points.
It's a sphere with like little holes in it. Yeah.
Points. Yeah.
No, good. That is very interesting and very relevant here. So do you have thoughts about what would be the problems for seeing this as scattering theory that kind of arise from that?
As long as you don't, actual asymptodia aren't really important to you. If it's just like quantum mechanics, in that sense, I don't, think it's a problem. If the domain of application is just what you usually use conformal field theory to do.
Yeah.
But I don't have further thoughts.
Okay. Yeah. So in the sense that usually we use it as, is what you're saying, usually we use it as an approximation to real scattering situations where, the outstates are, So maybe a question here is, why are we allowed to do that if there's no notion of far away or nearby? right? Why are we allowed to say that this?
Yeah, so you would have to explain what the relevant notion of isolation would be. That
Yeah.
This makes sense.
Yeah. I mean, do you think this is another kind of like? Well, we should talk about what. Maybe we should talk later. Like, it's an interesting question. Like, what would that relevant notion be, and whether they have kind of like spelled it out in a satisfactory way. Yeah.
So for a particular worldsheet, I mean, if you, again, going back to the discussion we had earlier, what you're interested in is a classical field, X mu field configuration to a classical X mu field configuration amplitude, right? There's none of this worry about that you have in perturbation theory of going about interacting particles and having to go asymptotically to sort of set up that S matrix,
Yes.
right? I mean, it's just a path integral that happens to be from these two sort of surfaces. It does make me realize I don't understand what happens when you then try and apply perturbation theory to the X mu field on the worldsheet.
Huh.
Right, because then you are back to having sort of particles in and out, and
Yeah. This is really
Okay.
interesting.
so there's something I don't understand.
Yeah. Huh, really? Yeah. That's. Thank you. That's a great comment. Okay. Very cool. So returning to Vistorini's point for a second, right? Okay. So Vistorini says you don't really have a quantifiable notion of proper time along tau. So I think that this is it's a fair point, and it is an interesting point. It's just a question of there are different interpretive puzzles you might want to solve with a given ontology for a theory, right? So let me distinguish two interpretive puzzles.
Whoa.
Oh,
We should make sure we have a picture of that.
oh yeah.
Already. Can you just write it lower down or something?
Yeah. I'll just write it elsewhere.
Don't write on that
Yeah,
wall.
try on this one. Can I erase this? Maybe that's the best thing to erase. Is this diagram.
You're hurting him.
I'm sorry. Okay. You can draw a diagram like that. At the side. Okay, so here's two puzzles. One puzzle is explain our experience of time and our sort of like time-dependent observable data that we collect. Right, so this is a puzzle that I take people in the primitive ontology tradition, like Maudlin and Shelley Goldstein to focus on, right? And they tend to think, well, you need ontology in ordinary four-dimensional space-time in order to provide a good explanation of this. Nick and Chris have a nice paper where they talk about other ways to try to provide such explanations in quantum gravity theories where you don't have that kind of background. But that's one puzzle, right? And another puzzle is essentially explain how to understand the concept of dynamics or change in a theory, right? I think that what Vistorini is pointing out is that Vistorini is pointing out that what she calls tau time is no help on this first puzzle, right? Because, you know, in all but the broadest senses, right, our experience of time and, you know, the sort of time-dependent observable data that we collect, you know, involves intervals of time occurring, right? Involves temporal distances or quantities of time, and that's not going to come out of the tau time. Now, that should be no surprise, because as Nick has pointed out in his work, the notions of space and time that show up in the sort of straightforward presentations of string theory, both the background space-time and one would also think that space and time on the worldsheet, those are all just a reduction basis for the space-time that we seem to live in, right? So this is Nick's paper called Target Space Does Not Equal Space. We're not looking for, from the fundamental ontology of string theory, we're not looking for an entity that is the time we experience. We're looking for a reduction basis for the time we experience, right? And then, you know, like, we got to tell the story about that reduction, but it's no dig against an ontology for string theory that it does not provide a quantity that is the time that we experience, because we would expect that to be reduced to the quantities that show up in string theory, right? So, I don't think this is necessarily like, I don't think history intended this point to be a dig against this interpretation. Rather, just a clarification of what the interpretation implies, and a caution, you know, that perhaps along the lines of some of the things we were talking about yesterday, along the lines of the space-time functionalist picture, we shouldn't necessarily understand the worldsheet as being like really a space-time. Or we definitely shouldn't understand as being, to borrow Tushara's term, an operational space-time. Right? That's pretty obvious. But now, right, here's another kind of puzzle. So another kind of thing that people sometimes say in quantum gravity is, for example, there was an evolution, and then, you know, like, so like in string cosmology, for example, people will sometimes say there was a phase change, and then space-time came into existence, right? And that can sound like gibberish, right? You know, it's like before there was space-time, there was like one phase, and then after that, there's a phase change, and then there's space-time, right? That's crazy. It sounds crazy, right? Because of course, how are you defining before and after without a notion of space-time? Well, the thought is that, and so this is a point that Noel and I want to make here, tau time can help with this puzzle, right? Because you can, essentially, the seeming incoherence of those claims about a phase change from there being no space-time to there being space-time, right? That's a puzzle about how do we understand the notion of dynamics or change in a theory where space-time is emergent. And essentially what this worldsheet first picture is saying is space-time is emergent, the space-time we know and love and live in is emergent from a different sort of space-time, right? The two-dimensional space-time of the worldsheet. And it's not a regular space-time, it's a conformal space-time. Okay. But that's fine, because, look, we won't have dynamics that involves, in a sense, like quantifiable change, right? Because we don't have a temporal metric in any sense, even a frame-dependent sense on the worldsheet. But we can say that there are events that are before and after, each other on the worldsheet. We have a temporal ordering on the worldsheet. Tau time does give us that, and so we can perfectly well make sense in tau time of claims like earlier in tau time there was no ordinary space-time, there was no space-time we live in, and then later in tau time there was the space-time we live in, right? So that provides a solution to this puzzle about how to understand dynamics and change when it comes to a theory where space-time emerges. So in that sense, I think this is the usefulness. So this is the usefulness of this worldsheet first picture were it to turn out to be true. Now, I raised a lot of concerns about like how I think there's a very good chance that it's not true. But it's a nice model to puzzle over. It's something that a lot of physicists have kind of hand-wavily gestured at. And if all we've learned is that this, in a way, attractive picture that people like, Witten and Polyakov have gestured at is not really a viable interpretation of string theory. That's progress because we get it out of the way and look for something else. Right? So that's kind of the moral of my story. Oh yeah, I felt like I wanted to have more discussion than last time. I think we had less, but
No,
we're
I
kind of
think
out of time now.
I think there was probably more. Or
Oh,
should
is
we-
it? Yeah, I guess it was more.
Should we
total.
take?
Yeah, that's true.
He's gone.
But it's yeah, we're out of time. Right?
But let's take. I mean, if people want to have questions
Yeah,
they want to
yeah.
raise for 5 minutes.
Is there anybody I haven't heard from yet? That'd be awesome too. Nobody I haven't heard
Call on people.
from? Yeah, right. Socratic method. All right. Yeah.
All right. So, just a quick, I guess it's a curiosity. So, in order to avoid central extension in the Virasoro algebra, we have this this parameter d that we usually interpret as the number of dimensions of target space. What would how would we interpret that in this worldsheet realism and sort of explain the central role it plays in string theory?
Right. Okay. So this is parallel to a concern you might have for Albert, really, which is like, why does the four-dimensional distance metric or the three-dimensional distance metric, we usually talk about ordinary quantum mechanics in separate space and time, why does that have such a seeming physical significance if this other picture of space is true, right? Yeah. So you might say there's a kind of like, you might say that that's something that the worldsheet picture would have to treat as a brute fact. And maybe it's not cool to treat that as brute fact, right? Yeah.
So it's the fact about the number of field operators we got on our worldsheet.
Yeah, I mean, like, yeah, right. So I don't know. It's a brute fact that like the quark field is, like an SU3 vector or whatever. So like,
yeah.
yeah,
Why not?
something like that'd be a
True.
brute fact.
True.
That's cool.